welcome to this problem walkthrough. Today, we will be tackling problem number 2222, titled Number of Ways to Select Buildings. In this session, we'll explore the problem statement, discuss different approaches, and break down the solution step by step. Let's get started. In this problem, we are given a binary string S of length n. Each character in the string represents a type of building, where 0 corresponds to a residential building and 1 represents a commercial building. The goal is to determine the number of ways to select 3 buildings such that they follow 2 specific criteria. First, the indices of the selected buildings must be in ascending order, meaning the first building comes before the second, and the second comes before the third. Second, the buildings must form one of 2 patterns, 0, 1, 0 or 1, 0, 1. The problem requires us to compute the total number of valid selections that satisfy these conditions. Let's look at an example to understand this better. Suppose the input string S is 0101. In this case, the output is 2. This is because there are 2 valid ways to select 3 buildings that meet the criteria. The first valid selection consists of the buildings at indices 0, 1, 2, which form the pattern 0, 1, 0. The second valid selection is the buildings at indices 1, 2, 3, which form the pattern 1, 0, 1. These 2 combinations are the only ones that satisfy both the order and pattern requirements for this input. Now consider another example where the input string S is 001101. Here, the output is 6 because there are 6 valid ways to select 3 buildings. The valid combinations are as follows: indices 0, 2, 4 form the pattern 0, 1, 0, 0, 2, 5, also form 0, 1, 0, 0, 3, 4, and 0, 3, 5, both form 0, 1, 0 as well. Additionally, the pairs 1, 2, 4 and 1, 2, 5 form the same pattern 0, 1, 0. These 6 combinations exhaust all possible ways that the buildings can be chosen to satisfy the constraints for this input. It's important to note that the input string S will always have a length of at least 3, so it's guaranteed that selecting 3 buildings is possible. However, due to the constraint that S can be as long as 100,000 characters, the solution must be efficient. A naive approach that checks all possible combinations of 3 buildings would have a time complexity of O n superscript 3, which is not feasible for large inputs. Instead, the solution needs to be optimized to handle the constraints efficiently while ensuring correctness. To solve this problem, we first considered the brute force approach. The idea here is simple: we iterate through all possible triplets in the binary string to determine which ones match the patterns 0, 10 or 101. Specifically, we look at all combinations of indices I, j, and k where I is less than j, and j is less than k. For each combination, we check if the substring formed by these indices matches the required pattern. While this method is straightforward and easy to understand, it involves 3 nested loops, one for each of I, j, and k. This makes the time complexity cubic, or O, n cubed, since we are examining every possible triplet. While this might work for small input sizes, it becomes completely impractical for larger strings, especially when n is as large as 100,000. This limitation prompted us to explore a more optimized solution. By shifting our focus to prefix counts, we can significantly reduce the computational overhead and achieve a much faster runtime. Now, let's look at the optimized approach using prefix counts. The main idea is to pre-compute how many zeros and ones occur in the prefix of the string up to each index. This allows us to quickly determine the number of zeros or ones that exist either before or after any given index. Using this information, we can calculate the contribution of each character to the total number of valid triplets. For instance, if we're looking at a 1 at index j, we can compute the number of zeros that appear before j, which we'll call count_0_ before j, and the number of zeros that appear after j, which we'll call count_0_ after j. The product of these 2 values gives us the number of 0-10 patterns where the 1 at index j is the middle character. Similarly, for a 0 at index j, we calculate the number of ones before and after that index to count 101 patterns. By using prefix counts, we eliminate the need for 3 nested loops and bring the time complexity down to O, n. This makes the method far more efficient and scalable for large input sizes. The key insight that makes this approach so efficient is realizing that using prefix counts allows us to calculate the contribution of each character to the total number of valid triplets in constant time. This dramatically reduces the overall complexity of the problem. The prefix count method is not only efficient, with a linear runtime of O(n), but also straightforward to implement once the concept is clear. Other alternatives, like dynamic programming, were considered but deemed unnecessary since the prefix count approach already achieves optimal time complexity without introducing extra space overhead or unnecessary complexity. When we compare the trade-offs, the brute force approach is easy to implement but far too slow for large inputs, with a time complexity of O(n cubed). Dynamic programming, while viable, would likely involve additional implementation complexity and space usage. The prefix count approach strikes the perfect balance between efficiency and simplicity. It leverages the structure of the problem to avoid redundant computations, making it the best choice for this task. To start solving this problem, we use a brute force approach to count the number of triplets that match the patterns 0, 10, or 101. First, we initialize a counter variable, count, to 0, which will track the number of valid triplets. Then, we use 3 nested loops to iterate through all possible combinations of indices I, j, k, or I less than j less than k. The outer loop sets the starting index I, ensuring there's room for j and k, while the middle loop selects the next index j, and the innermost loop picks the final index k. For each combination of these indices, we extract the substring formed by s, I, s, j, and s, k, and check if it matches either 0, 10, or 101. If it does, the counter is increment. This step ensures that every possible triplet is examined for a match. Once all iterations are complete, the algorithm simply returns the value of count, representing the total number of valid triplets found. For example, consider the binary string s equals 010101. Using the 3 nested loops, we generate all possible triplets of indices and check if the corresponding substrings match 0, 10, or 101. Each time a match is found, the count is increment. By the end of the process, the program outputs the total number of matches. It's important to understand the nature of these patterns. 0, 10, and 101 represent alternating bits, with 0, 10 starting with 0 and switching to 1, while 101 starts with 1 and alternates similarly. The algorithm ensures that the indices used to form these patterns are non-overlapping and in increasing order. The brute force approach works because it exhaustively examines every possible combination of indices, leaving no valid triplet unchecked. While this guarantees correctness, it comes at a cost. The time complexity is O(n cubed). With 3 nested loops, the number of iterations grows cubically with the length of the string, making this approach impractical for larger strings. However, for small strings, such as those with fewer than 100 characters, this method is feasible. In terms of data structures, the input string s is treated as an array of characters, which allows for efficient indexing and substring extraction. Meanwhile, the counter variable count serves as a simple yet effective way to track the number of valid triplets. This keeps the space complexity minimal, as no additional data structures are required. The key operations in this algorithm are triplet generation, pattern matching, and updating the counter. The triple nested loops ensure that every possible combination of indices I, j, k is considered, guaranteeing correctness. For each triplet, the algorithm extracts the substring formed by s, I, s, j, and s, k, and checks if it matches 0, 10, or 101. Since these are fixed-length patterns, the comparison is efficient. When a match is found, the counter is increment to reflect the discovery of a valid triplet. To improve efficiency, a few optimizations can be introduced. For instance, the loops can terminate early if the remaining portion of the string is too short to form a triplet. Additionally, unnecessary iterations can be skipped if s, I, is neither 0 nor 1, as it cannot contribute to a valid pattern. For more advanced approaches, sliding windows or dynamic programming techniques can reduce the time complexity significantly, bringing it down to O(n). These methods leverage the structure of the problem to avoid redundant computations. It's also important to consider edge cases. For example, if the input string is empty or has fewer than 3 characters, the result should immediately be 0 since no triplets can exist. If the string contains no matching patterns, such as in s equals 111, the result remains 0. Conversely, when the string is entirely composed of alternating bits, such as s equals 0101010101, the maximum possible number of valid triplets will be found. These scenarios highlight the need for careful handling of edge cases to ensure the algorithm is robust and accurate in all situations. The provided code efficiently solves the problem of counting the number of ways to select buildings that form the patterns 0, 10, or 101 in a binary string. This is achieved using a single-pass algorithm with constant space. We initialize counters to track the number of zeros and ones seen so far, count_0 and count_1, as well as the number of 10 and 01 pairs encountered, count_10 and count_01. These counters are used to efficiently calculate the number of valid triplets as we iterate through the string. The main loop processes each character in the string one by one. If the current character is 1, we add the count of 01 pairs to the result, since a 1 at the current position can complete all 01 pairs to form 010. We also update the count_10 counter by adding the number of zeros seen so far, as these can form new 10 pairs with the current one. Finally, we increment the count of ones. If the character is 0, the logic is symmetric. We add the count of 10 pairs to the result, forming 101 triplets, update the count_01 counter by adding the number of ones seen so far, to account for new 01 pairs, and increment the count of zeros. The algorithm runs in O(n) time, where n is the length of the string, and uses O(1) space. This makes it highly efficient for large input strings. By leveraging these counters, we avoid the need for nested loops, which would result in an O(n)³ complexity for a brute force solution. This optimization ensures that the solution is practical and scalable. Here, we start by defining the number of ways method, which takes the input string s representing the sequence of buildings. We first initialize several counters. The variables count0 and count1 keep track of the number of zeros and ones encountered so far. Similarly, count10 and count01 are used to store the number of 10 and 01 pairs we have seen up to the current point. Finally, we initialize the result variable, which will hold the total count of valid triplets like 0, 10, or 101. Next, we iterate through each character in the string using a for each loop. If the current character is 1, we add the number of 01 pairs to the result, as appending this one allows us to complete 0, 10 triplets. Then, we update count10 by adding the current count 0, as this one can form new 10 pairs with all previously seen zeros. Lastly, we increment count1 to reflect that another one has been encountered. Similarly, if the current character is 0, we add the number of 10 pairs to the result since this 0 allows us to complete 101 triplets. We then update count01 by adding count1, as this 0 forms new 01 pairs with all previously seen ones. Finally, we increment count0 to account for the new 0. After looping through the entire string, we simply return the result variable, which now contains the total number of valid triplets that can be formed. This approach is efficient, as we process the string in a single pass while maintaining the necessary counts to calculate the result on the fly. With this implementation, we achieve a time complexity of O(n), where n is the length of the string, making it well suited for large inputs. This concludes the Java solution for counting the number of ways to select buildings. We begin with the input string s equals 10101. Initially, all our counters are set to 0, count_0, count_1, count_10, count_01, and result. Now, for the first character, which is 1, we increment count_1 by 1 since we encountered a 1. At this point, no pairs exist yet, so the result and other counters remain unchanged. Moving to the second character, 0, we add the current value of count_10, which is 0, to the result, so the result remains 0. We then update count_01 by adding count_1 to it, which makes count_01 equals 1. Finally, we increment count_0 to reflect that we've seen 1 0. The state after processing the second character is count_0 equals 1, count_1 equals 1, count_10 equals 0, count_01 equals 1, result equals 0. For the third character, 1, we add count_01, currently 1, to the result, bringing the result to 1. Next, we update count_10 by adding count_0 to it, which makes count_10 equals 1. Finally, we increment count_1 to 2. Now, processing the fourth character, 0, we add count_10, 1, to the result, making it 2. We then update count_01 by adding count_1 to it, resulting in count_01 equals 3. Lastly, we increment count_0 to 2. For the fifth and final character, 1, we add count_01, 3, to the result, updating it to 5. We then update count_10 by adding count_0 to it, setting count_10 equals 3. Finally, we increment count_1 to 3. The final state for this example is count_0 equals 2, count_1 equals 3, count_10 equals 3, count_01 equals 3, result equals 5. The final output for the first example, s equals 10101, is result equals 5. Now, let's analyze the second example with the input s equals 000. Again, we initialize all counters to 0. For the first character, 0, we increment count_0 to 1. Since no one has been encountered, we don't form any pairs, and the result remains 0. Moving to the second character, 0, we increment count_0 again to 2, and the state remains unchanged with result equals 0 as no pairs can be formed yet. For the third character in s equals 000, which is also 0, we increment count_0 to 3. Even with 3 zeros, no consecutive pairs of 1 and 0 can be formed, so the result remains 0. The final output for this example is result equals 0. Next, let's evaluate the third example where the input string is s equals 111. As before, we initialize all counters to 0. With the first character being 1, we increment count_1 to 1. Since there are no 0s yet, no pairs are formed, and the result remains 0. For the second character, 1, we increment count_1 to 2. Even with two 1s, no alternating pairs can be created, so the result remains unchanged at 0. Finally, for the third character, 1, we increment count_1 to 3. Once again, no pairs of 0 and 1 exist in the string, so the result remains 0. The final output for this example is result equals 0. This concludes the walkthrough of the examples, illustrating how the counters evolve and contribute to the final result. The time complexity of this solution is O(n), where n is the length of the input string s. This is because the algorithm processes the string in a single iteration using a for loop. Each character in the string is visited exactly once, and within each iteration, the operations performed, such as checking conditions, updating counters, and assigning values, are all constant time operations, or O(1). When you multiply the n iterations by the constant time operations, the total time complexity remains O(n). Importantly, there are no nested loops or recursive calls in this solution, so the algorithm ensures that each character is processed only once. This makes the time complexity linear in all cases best, average, or worst since the number of iterations does not depend on the specific input beyond its length.